Having looked at some KC calculations, we can now look at some KP calculations. Very similar, just we're dealing with partial pressures rather than concentrations. So let's kick off. First example, our equilibrium there. And as with KC, we popped in the initial moles that we started with. We had 1 mole of PCl5, and we didn't have any PCl3 or Cl2, and they've told us that at equilibrium we have 0.6 moles of chlorine. So we put that information in to a little table. So that means that we have produced plus 0.6 moles of chlorine. So having produced 0.6 moles of Cl2, we must have produced the same number of moles of PCl3 because the ratio is 1 to 1 in the equation. And we must have lost 0.6 moles of PCl5. So we can work out how many moles we have at equilibrium. Once we've done that, we need to work out our mole fraction. And for that, we add up all those moles of equilibrium, which is 0.4 plus 0.6 plus 0.6 to give us 1.6. And the mole fraction is going to be how many moles we have divided by the total number of moles as we've done that. So if we work those out, we get the figures shown there. And now we can work out our partial pressures by times in by the total pressure, which is 625. And those gives us partial pressures. And then the final thing we have to do is put them into our KP expression. And once we do that, and we run it through the calculator, we will get KP to be 352. So it's just working out units now. So the units for the total pressure were in kilopascals, so the partial pressures were as well. And you can see that we will end up with our final units being kilopascals. So example 2, different equilibrium, and we've actually been told the moles of each gas present at equilibrium and Kp, but we need to find out what the total pressure must have been. So we put straight into the table our equilibrium moles, and we can now work out our mole fraction by adding up all our equilibrium moles, which comes to 1.02, and then dividing each equilibrium mole by 1.02, and we get those mole fractions there. And then we know that our partial pressure will be those mole fractions times by the total pressure, which we'll call P. And we can then pop those into our Kp expression, which is that one. So let's pop in our partial pressures of each of those gases, and we can multiply out the brackets there. And once we've done that, we can cancel our total pressures down, and we will end up with Kp as being equal to 3.37 times 10 to the minus 5 times P. We know what Kp is, and therefore we can find P to be 0.2012 atmospheres. Moving on to example 3 then. There it is. Have a look. I may want to have a go at this yourself, see if you can manage without going through the answers. So we know we've got 2 moles of SO2, 1 mole of oxygen, and we mix them and we allow them to reach equilibrium with a total pressure of 500,000 pascals. And we know that at equilibrium we have 0.67 moles of oxygen, and we have to find Kp. So let's pop in our initial moles as we've been given them, and also our equilibrium moles of oxygen. So we can now work out the equilibrium moles of SO2 and SO3. So we know that 0.33 moles of oxygen have reacted. Therefore, for every 1 oxygen, I need 2 SO2 molecules, and I produce 2 SO3 molecules. So I've lost 0.66 moles of SO2 and I've gained 0.66 moles of SO3. So I can put those numbers in, and now of course we're going to work out our mole fractions. and we know our total pressure, so we can also work out our partial pressures as shown there. And now it's just a matter of popping those into our KP expression and being very careful with calculators and so on. We can multiply those out and we will end up as KP being 1.929 times 10 to the minus 6. So now we just look at units. The partial pressures are in pascals, so our units become pascals to the minus 1. So that's taken us through 3 KP example calculations. Hopefully you found it useful. If you go to the website, you can download these notes, and also that will take you straight away to the full index of all the other topics that we cover, with links to the videos and notes, etc., which hopefully you'll find useful.